Here's a mind-bending mystery in the world of exoplanets. Why do so many sub-Neptunes, planets larger than Earth but smaller than Neptune, show puzzlingly flat spectra when observed? This phenomenon has left astronomers scratching their heads, as it seems to defy our understanding of planetary atmospheres. But here's where it gets even more intriguing. The solution might lie in something surprisingly simple yet overlooked: clumpy aerosol distributions in their atmospheres. Transmission spectroscopy, a powerful tool for studying exoplanet atmospheres, was expected to reveal the chemical compositions and origins of these distant worlds. However, many sub-Neptunes display flat near to mid-infrared spectra, which traditionally suggest either metal-dominated atmospheres or high-altitude, gray aerosols. But here's the catch: observations of escaping hydrogen and helium from these planets rule out metal-dominated atmospheres, while uniform distributions of small aerosols fail to produce the observed flatness. Larger particles, on the other hand, would require production rates that defy physical laws. So, what's really going on? In this groundbreaking study, researchers James E. Owen and James Kirk explore the role of heterogeneous, or clumpy, aerosol distributions in shaping these spectra. They find that moderately optically thick clumps of aerosols at high altitudes can indeed produce flat spectra, even with small particles and realistic production rates. And this is the part most people miss. Clumping increases the effective path photons travel while reducing wavelength dependence, effectively turning the aerosol distribution into a gray absorber. This mechanism elegantly resolves the tension between flat spectra and low metallicity atmospheres. Applying this framework to the Sub-Neptune TOI 776c, the authors demonstrate that clumpy aerosols can explain the observed flattening of its transmission spectrum, aligning with a primordial He-dominated atmosphere. They also discuss how this clumpy structure could influence emission spectra, potentially creating observable signatures due to enhanced stellar radiation penetration and altered scattering. These findings suggest that clumpy aerosol distributions may be a common feature of sub-Neptune exoplanets. But here's where it gets controversial. If clumpy aerosols are indeed the solution, it challenges our current methods for interpreting exoplanet atmospheres, particularly with advanced tools like the James Webb Space Telescope, JWST. Does this mean we've been misinterpreting spectral data all along? And what physical mechanisms could generate such clumpy distributions in the first place? These questions open the door for exciting theoretical and observational work. Broader implications of this study highlight the critical need to consider aerosol heterogeneity when studying high-altitude microphysics and the spectral appearance of exoplanet atmospheres. It also underscores the importance of theoretical advancements to understand the processes behind clumpy aerosol formation. What do you think? Could clumpy aerosols be the missing piece in our understanding of sub-Neptune atmospheres, or is there another explanation waiting to be discovered? Share your thoughts in the comments. Let's spark a conversation that could shape the future of exoplanet research.